Okay, great. Can everyone hear me? So thank you all for joining us today for our final talk of this spring Design++ seminar series. Yes, I would like to make a general overview of an introduction to the seminar series. We host it every spring and every fall. This is our group of this year or this semester who has organized the seminar series for you. And if you have, and I wanted to ask this very explicitly, especially as we start to plan for the fall, if you have any ideas for speakers or topics that you would like to hear next year or next semester or even next year, please get in touch. So you can reach out to anyone listed here. Here's an overview of our agenda, of who we've heard from throughout the year. And then if you happen to have missed a talk that you would like to then go see, including all of our talks, which we've hosted now for the last 3.5 years, we have a growing and a very large archive of talks that you can look into. Now, so for today, we're very happy to welcome Professor Bernd Bickel as our closing event. And this, I would also like to note that it's a joint event with ITA, the Institute of Technology and Architecture, as I would also like to welcome, and the opera will be a special welcome for him to the Institute. So as you may or may not know, Bernd joined ETH in February this year as a professor for computational design within the departments of architecture and also affiliated with the Department of Civil Engineering. And so, yes, as I mentioned before, within De Arc, he is welcomed here in ITA. And his professorship is also embedded within Design++. So this is also a very nice event for us as well. And so originally, Bernd is a computer scientist, and his interests are in computer graphics and how they overlap with robotics, computer vision, machine learning, material science, and digital fabrication. As we will hear in his talk today, his main research objective is to push the boundaries of how digital content can be efficiently created, simulated, and reproduced. And so I'd also like to note that although Bernd started here only a few months ago, we've had, I think many of us have had the pleasure of already interacting with him on proposals, projects, and things, various even events. So we would like to extend a very warm welcome, and we're looking forward to your talk. Thank you.
Thank you, Danielle, for this very kind introduction. Today, I will talk about rethinking design and fabrication with computational and data-driven methods. And the reason why I think, and I hope it does not require much to convince you as well, why this topic is extremely exciting is because design is everywhere in everything that we need to create. It's in buildings, in everything that engineering creates, in material structures, in chemistry, think of new molecules, but also, of course, for example, in computer graphics and animation, that's the area where I'm very originally coming from, for example, when designing a new character in character rig, and also in computer science, for example, in the form of data structures, neural network architectures, programming languages. So even writing a program, you can see as a design task. Now, one challenge with most of these designs is that with just a few exceptions, that they, to a large extent, need to be manually created. So I think across all these application areas, there is one very central question, which is how can we more efficiently do design? How can machines create complex designs, and how can machines work together with humans to create designs? What are actually the key problems such that machines and humans are actually successful in finding good designs, exploring design spaces, and even discovering good designs faster, or new designs that might not be discoverable or doable by hand? I also think this topic is extremely timely. So we're all witnessing this omnipresent rise of technology in all fields, be it construction, architecture, urban planning, arts, crafts, of course also in computer science. And in particular, we see this exponential acceleration of AI. So our research is motivated by the belief that there is really an urgent need to harness the potential of technology while at the same time also preserving the human creativity and the creative process. And so basically with this, ultimately give humans superpowers to do design. And we do this in my group actually by focusing on 3 areas, which is simulation and optimization, spatial computing, and AI. And in the following, I want to give you, a few examples actually of work that we did in this area in the past. So what I will do is I will start with presenting a procedural method for modeling metamaterials, which empowers humans to accurately model a wide range of materials in a forward modeling fashion, meaning there is very direct control of modeling these materials. And then I will switch gears and look at 3 very different types of approaches for doing inverse modeling. So we'll start with a general simulation-based approach for optimizing CAD models. Then I will show how geometric models can actually help with describing design spaces, in this case, in the setting where we look at active bending, and this is used to design these pavilions. And then finally, I will actually conclude by showing how 3D wire sculptures can be easily designed using a text-based approach. So basically going from just a semantic description to a 3D model. And yeah, these projects, I picked them because they show very different strategies basically on how to approach a design problem. Okay, so with this, let's start with the metamaterials. So a metamaterial is a mesoscale structure that has been engineered to exhibit a very specific behavior. And by changing the shape of this structure, we can actually realize a wide range of properties, such as in this example, for example, elastic behavior. And we can tune this with the material structure. Now, metamaterials are a big topic of interest in science and engineering. Previous work, for example, used metamaterials to create things like single material 3D prints with spatially varying elasticity. Researchers have also looked into metamaterials for other properties, such as, for example, sound waves or blocking sound waves, blocking certain frequencies, more efficiently, for example, dissipating heat, or also mimicking certain biological structures like bone-like structures and so on. Now, these diverse and growing applications are very exciting, but they also rely on our ability to very efficiently design these metamaterials and explore this space of metamaterials. So unfortunately, doing this is quite challenging because it's difficult to parameterize all these diverse structures you see here in a unified manner. So what you could do is you could use a very general representation, for example, voxels. They can basically represent any kind of structure, but it's then very challenging to manipulate these voxels and explore the design space because you have so many of them. You have millions or billions of them. So instead, what engineers usually do is they turn to a class-specific representation, like, for example, meshes or level sets or graphs or a constructive solid geometry to somehow create them. But the problem is that these representations itself are not really compatible with each other. So you somehow need to choose something and then really stick to that representation, and you're somehow then confined to what you can do with that very particular representation. So to address this issue, we actually proposed a new representation that is node-based. It's a procedural graph representation where the graph, we try to come up with a graph that is really small and that is easy to edit. And also, of course, on the other hand, we wanted to have this graph being really also very expressive, so being able actually to really recreate all these kind of structures. Now, let me very quickly show you how this works. So at a very high level, our approach uses a set of operation nodes to first define small skeletal pieces of the target structure. And then there is a series of transformations like mirroring, rotating. And with this, actually, you build up the object. And then there's a thickening operation. You have your metamaterial structure. Now, you might ask, why solving this problem in such a way? So I think this representation offers quite a few nice advantages. First of all, starting with the fact that it really capitalizes these features, how usually microstructures are built up, such as symmetries and so on. This comes very natural. And also the representation preserves the construction process. So we have this step-by-step process, which makes it easy to understand what is going on, and it also makes it easy to edit these structures. And so as a proof of concept, we've actually built a small cat-like system around this representation that allows people to build these microstructures. And there's also a simulation component in it, where then when you have designed a structure, can also even very quickly evaluate what are the actual properties of this structure. Now I want to very quickly show you how this works, and then also, point you to somehow the technical highlight that was the challenge in actually really building this. So this procedural graph is composed of 14 different nodes. This includes some basic geometric transformations, thickening procedures, and Boolean operations. We have a handful of nodes for integrated property prediction. But then actually the most critical part of the representation is this skeletal design space, which allows us to build these fundamental skeleton pieces in the first hand. And we do this actually by instantiating line and surface skeletons over a set of vertices and end edges. And now, such that this is sufficiently rich, so that we can really have this very representative or expressive space, we somehow must ensure that this really can represent basically these 5 big major shape classes for metamaterials, which are straight trusses, curved beams, planar shells, curved shells, and also solid bulks. So we actually worked here also together with material scientists to really have a good coverage. And now it turns out, and you can believe me, that basically the straight trusses, the curved beams, and the solid bulks, they're quite easy to model. We can somehow manage this. And what I want to do is now, in the following, I want to dig a little bit deeper into one of the remaining classes, which are shells. So shells it is a very, very important class for metamaterials. And there we want to have planar shells and also curved shells. So I want to show you a little bit how we approach this. So let's first look at the planar shells. So there, the skeleton is a simple hexagonal plate, for example, in this example. And it's quite easy to build this by actually specifying an edge loop that matches this boundary. And what we simply do then is we implemented a direct surface solver that considers as input this edge loop, and then just basically with a thin shell simulation basically infers this surface here. And if you then tile this with geometric operations, you, for example, get this microstructure. So that was quite easy. Now we can try to step up the game, make this a little bit more complex by actually providing now a loop whose vertices are not coplanar, but look like this, for example. And you can also, again, use this thin plate solver, and you get a surface that just looks like this. And if you tile this, you actually get a structure called the Schwarz-D surface, which is actually a very famous metamaterial structure. It's a triply periodic minimal surface, TPMS here. And also this comes more often in the talk because these class of structures are actually, they have very good physical properties, so they're of special interest. Okay, so now with this, we can also build this kind of structure. And when we did the project, at this point, we thought, okay, cool, awesome, we were done. We already wanted to open champagne bottle. And then the first author student, Eliane, actually, she did a test with another TPMS structure, this Schwarz-P surface. And unfortunately, it turned out that this approach did not work as intended. So this is the structure, how it looks like. It's also a very famous structure. And you actually can see the boundary is now, has this curved boundary. So that's how it's put together. And if you use, again, our a solver, basically specifying these boundary edge chains, and you solve for this surface, and then put it together, things do not go as planned. So here, you need to look a little bit carefully, but probably you can see it. So there's suddenly these weird discontinuities when you put these surfaces together. And smoothness is actually a very important characteristic of these microstructures. So it means that does not work. It's actually not really usable. Yeah, so back then we were quite disappointed. And we actually said, okay, we really want to have a system where the user just marks a couple of salient points. Basically where the surface intersects this piece. And then based on this, we really wanted be able to infer this surface. And then we basically banged our heads against the whiteboard for a couple of months till Lian actually came up with a really cool insight. And there the idea is basically, and I just explained this very high level, to go through an indirection, and actually she came up with a solver based on the conjugate surface construction method. So what this is actually, it's an indirect solver that explores the fact that each of these minimal surfaces is actually very directly or intimately related to another type of surface that is actually bounded by a polygonal boundary. And this is basically this conjugate surface, and once you have one, you can actually find a transformation to the other one. And this is easy to solve. So basically the way it works is there is this conjugate surface construction method where you actually, you have the input of your high-level problem, then you actually define this conjugate polygon. You solve there for a minimal surface, and then you can transform this back and actually get the target surface. And I mean, this method was around in the literature, in the math literature for 50 years. So this is the math literature well known. But the problem was so far it was really not usable for design. Because the problem is you need to define this conjugate boundary, and you only see the result after you have solved the surface and basically got this target surface. So if you try to do this by hand, it's very difficult to come up with the conjugate boundary. What is really the boundary you need that you get the desired target surface? So doing it by hand is basically impossible. And what Lian did is then she came up with an optimization loop that basically automatically computes this conjugate boundary and optimizes this so that you get the desired target surface. And so with this, actually, she made this method accessible for the very first time for design. And this is now really, really cool because, for example, now this Schwarz P surface, with this method, we can really construct this metamaterial, and this truly works. And you can do even more with this. For example, you can do small changes. In this example, for example, we moved one vertex and added one vertex more. And when you have this conjugate surface, you can actually turn this into another very well-known TPMS structure, which is called Waves genus 4. And this flexibility now, doing these small edits and then getting these very different special types of microstructures is actually something really cool that did not exist before. And so with just, for example, doing a little bit of random perturbations, you can generate this family of different microstructures very efficiently. And yeah. And as I mentioned, I mean, this is exciting because these TPMS structures, they have very amazing trade-offs, for example, between stiffness and density, and they actually approach theoretical upper limits that are there. And they're also great for additive manufacturing because they are actually self-supporting structures. And now by basically unlocking these TPMS variations, we can suddenly do much more and explore, thoroughly this design space of these promising structures. Yeah, and then basically I want to zoom out here. So I talked now for a long time about shell-like structures, but also with this graph representation and these other types, we actually now have a representation where we really can combine these different types together and have actually these very small graphs describing these microstructures, and with this actually building quite complicated microstructures across the different families. And it's also cool, I mean, we tested this representation and this CAD system with users. So for example, we gave them a couple of microstructures and asked, hey, can you reproduce them with our system? And it turns out, so we had 10 novice users, never modeled a microstructure before, and within an hour, they were all able to reproduce all these microstructures. So it's also intuitive to use, and also they're easily, for example, tileable, also 3D printable, so these are 3D prints. And yeah, and then we, for example, also examined the properties of these structures that we've built so far, that we found either by manually creating them or just having these random perturbations. This actually covered a quite nice range of material properties. Oops. Yeah, and also, I mean, we looked at different applications. I mean, one is, of course, stiffness, but we also played, for example, around with phononic band gaps, where, for example, you can filter out certain acoustic frequencies, and also that actually worked quite nicely. Now, looking forward, we believe that here, first of all, more thorough exploration of this, gives you really new opportunities for metamaterial development. There's also, I think, a lot of, I mean, so far this was a forward modeling process, right? So either the user directly modeled it, or we just randomly, changed a couple of parameters. So doing inverse design now by more systematically trying maybe to optimize these parameters for certain behavior, I believe has a lot of potential. And also just extending this representation, for example, with different thicknesses or other types of base shapes that you tile together would, for example, be low-hanging fruits that I think could give you quite nice opportunities for future work. Yeah, now having mentioned actually inverse design, I want to now switch gears and start looking at some inverse design methods. And I want to start with a simulation-based approach. And basically an important practical step towards the goal that humans and machine can efficiently co-design is actually, I believe, an optimization method that does work with parametric surfaces. I mean, probably you as audience, you don't need to be convinced, but basically all popular CAD tools work with parametric surfaces, and they're the representation of choice for many engineering applications in construction, robotics, architecture, and so on. And I mean, these parametric surfaces are around for a long time, and there's a reason why people are using them, because they allow you to really mathematically, precisely define surfaces and also things, for example, like holes or so, that they really come out perfectly. Yeah, and basically, if one, after now somebody, for example, has designed such a CAD shape, if you want to do design, you usually also want to test how does it behave. So typical workflow is that you start from a parametric CAD model, as you see on the left, and then you want to test its behavior in simulation. And for doing this, usually you have to mesh this model to run a simulation on that domain. And there, for example, you can then use finite elements to test, for example, occurring stresses, just to give you an example. And because we want to optimize the model, now, of course, based on the analysis, the model has to be updated. And so basically what we want to know is, how does our analysis, the performance of the part, change with respect to small changes in the CAD model itself? And for this, we want to actually have this process to be ideally differentiable and smoothly differentiable. And the big problem is that, unfortunately, in a general case, this is not the case here. So the problem is that with each update that you do, for example, when you enlarge the hole, you need to create a new simulation mesh in each step. And meshing itself, first of all, is difficult. So that's already a painful process. But even if that works because your mesh combinatorics change, this is usually not a smooth process. And you have some noise in there, which actually makes then your optimizer not work very well. So we thought, okay, we want to really address this problem. And so we came actually up with a pipeline that allows you to easily optimize CAD models automatically. So the way it works, we start with a CAD model as an input, and then we parameterize it, basically telling the simulation which high-level parameters of the model can be changed. And then at the core of the system, which is also the main contribution of this work, there we have an analysis based on the XFEM method, which is actually fully differentiable and allows you to do fully automatic optimizations of the model based on certain objectives. And then as an output, we actually get this optimized CAD model, which can then be, for example, directly further be used in your CAD workflow, and you can, for example, then still manually edit it. Now, I don't want to spend too much time on how it works, but I just want to give you, a quick flavor of it. So first of all, in terms of the simulation, the underlying method is an XFEM method. That's basically an extension of the classical finite element method, where your simulation mesh does not need to be exactly correspond to the boundaries of the object that you're simulating. So basically, you can just take your object, put it, for example, into a regular grid, and it's fine if actually for certain elements, parts of it are inside and parts of it are outside. So this method works in that case. And so basically, you don't have a headache about meshing, and they need to find a mesh that exactly conforms to the object's surface itself. But as always in life, there is no free lunch, unfortunately. So there is still basically the challenge that we need to integrate certain quantities over the object itself and over the boundary. And this can be a challenging problem. If you look, for example, at this model here, this might be quite tricky to do these operations precisely. And basically what people usually do is, you need to find so-called quadrature rules so that you can evaluate these volume and surface integrals efficiently. If you only do this for a static model, that's fine. You can invest some time for finding these weights and pre-computing them. But the problem is, we actually want to optimize the model, so it always changes. And with this, we would actually need to also recompute these integration rules all the time. And so this makes it quite challenging. And so what's quite nice is here that one of my former PhD students, Christian Hafner, he came up actually with a very elegant method for solving this. Just very high level, the way it works is he's using this divergence theorem where you can actually, you have, for example, this quite complicated volume, and you can break this down into now surface integrals. So you basically can look at the patches, how this volume is confined, and then instead of computing this volume integral, you can, with the divergence theorem, compute the surface integrals. And you can now do this nested rules, so you can actually break this down into then, the surface into flat patches, and then these area integrals on these flat patches, you can again look at line integrals and then just compute these values of these line integrals and then somehow propagate this back. And by doing this, actually, you can super efficiently and very accurately do this integration over complicated domains. So that the details are not so important here, but it somehow, in the end, this was sort of the core secret so that the overall system worked really well. So I wanted to briefly point this out. And it also turned out that this scheme now works also much more efficiently and also more accurately than what was back then state of the art. Okay, now with this, basically, we can very efficiently run optimizations and also compute derivatives. And so I want to now just touch on a second important topic for doing these optimizations, which is actually that we need to somehow specify what part of the object or what should be optimized. Because basically a good parameterization should give you sufficient degrees of freedom to enable meaningful improvements of the objective while actually preserving the original intent or the designer's intent of the object. And so usually on a low level, for example, you have these control points that define your surface, and you don't really want to optimize directly on these control points, because if you start moving them around independently, you get something that looks very ugly. So instead, basically, what you want to do is you want to define some high-level parameters, for example, the radius or the center of a hole, and then go from those to the low-level parameters. And basically with this, you can always, to some extent, keep the shape or somehow the designer's intent of the model. And this is one piece of the ingredient. And then we just also realized, unfortunately, if you just do that alone, it's still not sufficient, because the thing could be, for example, if you have such a rounded off edge, and you now start moving, for example, the center of this cylinder that defines basically the radius of this rounding. If you start moving this around without taking care of neighboring surfaces, you again also start breaking the model. So in the end, basically, the second secret ingredient was what you really need to do is you somehow, when you load a CAD model, you actually need to look at neighboring surfaces and basically extract constraints there and figure out which ones of, for example, these tangent constraints you need to keep and which ones are not important. And in the end, basically, what worked really well for us, we just came up more or less with basically a lookup table. And so you load this, you get these tangency constraints. And then now putting all of this together, you can now really nicely optimize models and making sure they don't break apart. So I want to very quickly show you some examples of this. So let's start, for example, with a very simple wrench here. And as you can see, even that model has quite a few tangency relationships along each edges, which need to be preserved. And what you want to optimize in this example over are actually the slot, the hole, and the fillet radii. And here you can now see how this model is first loaded into our tool. And then it automatically finds these constraints and then optimizes it, for example, for improving the strength to weight ratio. And once this is done, you can again load it back into your CAD workflow and also further edit it if you want. Here's another example of this. So here we optimized an asymmetric wheel rim. And here we had several objectives you want to optimize for at the same time. For example, the center of mass needs to be exactly where you mount the wheel. Also, the inertial axis needs to be properly aligned so that it can spin stably. And we also optimize the strength to weight ratio under a certain load. And you can now, with this tool, very, very easily do all of this. And this is an example where we then 3D printed the result, and you can see this optimized wheel rim now spins stably, whereas the other one, the initial starting point doesn't. Here's another fun example, a fidget spinner, where we also optimized for a stable spin here. Yeah, and then basically, quickly summarizing that part. So, I mean, this is a very general framework for optimizing the performance of a part. And while in general, this works well, it has certain limitations. For example, it cannot handle topology changes, for example, or material interfaces. But of course, another important challenge is also speed. So this is really, really slow, right? Because if you have a large model, you have many elements, it takes a very long time. So it's not really interactive. So what we also do is we actually for many approaches, we look into actually how can we speed this up significantly to have a much faster performance and allow, for example, also interactive form finding that also, to find shapes that have a certain performance. And I want to show you just very briefly one example here. So we looked actually quite a bit at active band elements. I think they're quite intriguing structures. They have a very long history, even starting thousands of years ago from these Turkmen tents. And also they have actually quite aesthetic appeal, and they're quite widely also even studied by mathematicians, but also designers and architects. And yeah, we looking at this, we started asking basic questions like, how can we do design for active bending? Can we learn certain basic properties? How can we explore this design space to actually find shapes that work well under an active bend? And here, just show a few videos. So in one of our projects, the goal was actually, we want to design flat, flexible panels that have actually a tailored mechanical property such that when you assemble them, so just basically put them together, they achieve a certain shape. And here you see an example. For example, if you put this sheet together, you actually get a sphere in the end. And the system actually triggered quite some interest. So there's actually a partner at the University of Pisa and also the School of Architecture at the University of Technology, Sydney. They actually used our system that we initially created for small pieces and actually started designing pavilions with this. And basically here, just very briefly, what the workflow is, you start with a shape, you analyze the curvature on the shape, place a cross field on it, then there's a quad meshing, and then basically there's a software that splits these meshes into quads, and then these quads into patches that are actually manufacturable at a certain size. And then at the core, actually to tune the mechanical parameters such that you get actually this desired shape that is in equilibrium, when fixing it. The way it works is that for each quad, you actually have this cross, and then you start basically twisting it. And with this, you tune the mechanical property of it. And we have a data-driven system, so pre-computation actually that says, now for a certain configuration, how are the forces when this is stretched, when this is bent, and also when these structures are twisted. And based on this, the system can then very efficiently actually do this optimization, actually try to find mechanical, basically configurations that have these tailored mechanical properties so that this system, that it gives you actually the desired shape. And once you have found this, now for this pavilion here, you can easily manufacture it with milling. It also conveniently fits into boxes for shipping. And then here in this example, the students actually assembled this structure at the International Architecture Exhibition in Venice in 21. Yeah, it takes a bit till it's in full shape, but then in the end, that's how it looks. And also here is another shape that actually was created basically by two collaborators at UTS, Nico Pietroni, and who's in computer science, and Tim Schork, who's a professor there in the School of Architecture. Okay, with this, I want to now again switch gears and actually come to the very last project that I want to show you. So far, we have seen methods that require actually quite exact specifications or goals or targets of what you want to design. And I think now one interesting question is, how can we actually achieve similar things but with much more abstract descriptions, like, for example, text. So in the following, what I want to show you is a system that allows you to go from various types of inputs, like for example text or also photographs, to 3D wire art using a computational design algorithm. So here, for example, you type in giraffe and elephant, and you get this wire sculpture, 3D wire sculpture out of it. And basically in practice, I mean, there are several challenges, related to a wire art creation, but in this project, we basically focused on two, I think, probably most relevant ones. One is this problem of abstraction, and the other one that we also, in the end, get a structure that we can actually fabricate. Now, the abstraction is about designing a wire shape, and the challenge here is that usually this wire art doesn't come as an exact description or something that we can exactly replicate, for example, from a 3D shape. So, usually you want to start with a reference image or with a high-level concept, and then you somehow want to convert this semantic concept into a 3D shape. And I think it's actually not very obvious how to do that, because you don't really have a target you can optimize towards. And then the second challenge is, of course, the fabrication of the actual wire bending. So even if you have somehow virtually the perfect shape, how can you make this wire? So we generated a system that tries to overcome or address these challenges. And basically, the approach is the following. We take as input images or text, and from this, then automatically generate curves that represent this input. And then for fabrication, we generate 3D jigs that actually we can 3D print, and with this actually put the wire through and get the actual sculpture. And I want to just very quickly explain you the algorithm, how we actually model the curves or get the curves. So what we do is, in terms of representation, we try to get the curve through a continuous optimization. So as a representation, we have actually a continuous 3D curve, and we start with something like, for example, this loop here. And then during optimization, we have a differentiable rasterizer to optimize the wire parameters, so the parameters of this curve directly. And I mean, a reason for doing this, or why this is a good idea, is because if you always have a connected curve, somehow, you don't get individual pieces that are hanging in the air. You always have like some continuous, nicely connected structure. And now for the loss, what we do is we have a clip-based loss, and I'll explain you this in a second, how this actually works. And then with these ingredients together, you can go from this text input, for example, to this shark model. And here you see how the optimization goes from this initial curve to the 3D model. Just again, so this is basically the same concept as before, showing you in a loop. So basically we have this 3D curve. We can somehow evaluate an error that is differentiable. We can backpropagate these changes and then iteratively basically optimize this curve. And we have two error components, one for the visual approximation and the other one for fabrication. And now for the visual one, the way there it works is, so we got inspired by some recent work on sketch generation methods that overcome this domain gap between 3D curves and text, by evaluating the rendered curve using some pre-trained vision language model. So the way it actually works is, so for this we build on a CLIP, which stands for Contrastive Language Image Pre-training, which is actually a deep learning model that was developed by OpenAI in 2021. And it's trained on 400 million image text pairs collected from the internet, with the objective of creating a common latent space where you can actually encode both text samples and images together. And in this space, in this representation, you can then also compare these things. And what is great about CLIP is that it's really exceptional also in encoding the semantic meaning of visual depictions, regardless of their style. So whether you have drawn a banana or high-res image of the banana, for example, it always somehow realizes, okay, the semantic meaning, you have a banana in this image, for example. And we basically, we use this approach, and with this we define an error metric. So what we do is actually we have our curve, the parameters of our curve, and then the way it works is you render this. So you render a couple of images from different viewpoints. And then these images, you can actually now use this clip-based method to get an embedding of our sculpture in that space. And you can do the same actually for text. So you also, basically this text description, you also have an embedding now in the same space. And then you can simply, these two embeddings, you can look how different are they, and they give you basically a meaning of like, how close or how far these concepts are away. And the really cool thing is that this is agnostic to low-level features such as pose or structure, this embedding. And it's, of course, also it's differentiable. So you can also now, this now suddenly this connection between the parameters of your curve and how close is this to your text. But you can also, with this, because it's differentiable, you can figure out, okay, if you now want to make this difference a little bit smaller, how do you need to change the parameter to make this error metric smaller? And so basically then this is one component of the optimization, and the other one are just some fabrication constraints to make sure the curve is not too extremely bent and so on, so that you can also really make this sculpture in the end. And then once again, if you put all of this together, as you've seen before, you actually quite magically get this 3D optimization of this sculpture. Just very briefly also how we manufactured this. So here you now see one of these 3D printed jigs and how the student is actually now putting the wire through it. Unfortunately, we have to destroy the structure in the end. Maybe this like follow-up work to maybe be creative and come up with a way of making this also reusable. And then with this, here's another example where, for example, we have 3 words as input: cat, dog, and bird from different viewpoints. And with this, actually, it optimized this 3D structure that really, from different viewpoints. Before it looked like a cat, now like a dog. If you rotate it around, here, it actually does resemble a bird. Here's some more examples of this. And and as you can see, it also works with image input, or what I think is an easier case is also if you already start with a 3D model. Good. So with this, I'm now ready to wrap up. So I presented you a project that solved design challenges based on 3 very different technical approaches. And just to very briefly contrast them here. So first I presented an optimization-based approach, which allows very precise differentiable simulation to optimize CAD models while maintaining actually, or trying to maintain the designer's intent of this CAD model during the optimization. Second one that I just touched very briefly was a data-driven approach combined with some geometric characterization that allows to quite quickly do form finding for these active band structures. And then finally, a semantics-driven approach, which is based on a very general text-image model that was actually able to drive a quite specialized application, this generation of 3D wire art. And here, I think the very amazing thing is that probably, this clip model, this text-image model, with the 400 million images, I would doubt that it has seen, many examples of wire sculpture and text. So there was probably almost nothing there, right? And still it could somehow, you could use, the semantic information and then, use it to drive actually a particular application. So I think this is actually quite exciting and promising direction that also can potentially be explored further, where you can actually think of, okay, yeah, you use a very general model, but then somehow combining it with some more traditional representation, and with this really create maybe very new types of user interfaces to drive design tasks. Now just a few very general words. So overall, I truly believe that this area of computational design is an extremely exciting area, and probably one of the most exciting areas I believe you can be in the next decade. And making significant progress in this area really requires, in my opinion, not just an either-or, but really a comprehensive understanding of core technologies in computer science, such as simulation and optimization, data-driven methods, algorithms and data structures, and machine learning, and then really combining them in a smart way with applications areas, and in the end also really putting the user in the center. And I think the future is really, really exciting, because bringing together basically this world of traditional workflows with advanced robotic fabrication methods that become more and more autonomous, mobile, and also versatile. I think many of you are actually working in that direction, which really vastly extends what you can build, and also in terms of efficiency, what you can build, more sustainable materials and so on. So this is super exciting. Also maybe exploring more this metamaterial direction there. Combining this with unlocking the power of AI, especially creative AI, systems where humans and computers can work together for finding new designs. And then also combining this with AR and VR, which is also another technology which is on the verge. So very basically have a new compute platform for immersive design, very new ways how people can collaborate with each other, also do augmented construction, for example, at scale, and also potentially having a device where if it's widespread, where you can, with your technology, potentially reach billions of users. So I think putting all of this together is extremely exciting, and really allows, gives us a unique position to rethink the field together, and also developing sustainable solutions for the future. And actually, I want to end my talk with a quote from John Lasseter. So actually, when I was a postdoc, I worked for the Walt Disney Company, and back then John Lasseter was the creative officer there at Pixar and also at Disney. And he basically summarized the philosophy at Pixar as art challenges technology and technology inspires art. And I want to invite all of you to basically do the same. So let's together, first of all, let's challenge technology, but also let's together develop technology that really inspires our field. And yeah, I'm extremely excited to be here at ETH, having these opportunities, and also hopefully having many opportunities to work with you together and explore this very exciting area. So thank you very much. Oh, and I'm very, very sorry. Actually, I forgot basically the most important thing. So I want to really, thank all my collaborators and wonderful students. Basically, all the credit of the work, should go to them. I mean, they worked incredibly hard on these projects, and they did the heavy lifting, and so I want to really give appropriate credit to them. And of course, also to the funding agency. Thank you now.
Great. So thank you very much for this informative talk and very inspirational ending, in particular with this quote you finalized your talk with. With that, I would like to open the floor for questions. Does anybody have a question that they would like to start with? I think everybody's still digesting what they just learned and what they just saw. But what I could, yeah, Christoph?
So thanks a lot for a really interesting talk. It was actually nice to see the summary of the work. You talked about a lot about differentiable problems. And I believe in our institute, we use a lot of non-differentiable simulation models. Do you have approaches to automatically make non-differentiable problems to differentiable problems? Is that something you have an idea to how to do that?
I mean, that is not super easy to do. I mean, there's ways like, finite differences. For example, it's a standard approach you can do. I mean, there's ways of, things that also we did in our group is you can try to, for example, come up with a surrogate model and then basically train that, making sure also that this surrogate model is in some sense differentiable. The thing is simply if you have a continuously differentiable model, it turns out these are usually much easier to optimize. Of course, you have the danger sometimes, that you run into a local minimum and then don't find like a globally optimal solution. But the very interesting thing is, and people have seen this also now with neural networks and so on. So if you go to very high dimensional problems, somehow magically, it seems you can avoid, some of the local minimas. So, in the end, what my experience is if it's possible, I'll try to, map a model to something that is continuously optimizable, or that you do like tricks like there's, for example, also tricks like relaxation where maybe you have a problem that only has certain discrete solutions, but during the optimization you simplify the problem a bit by allowing somehow continuous solutions in between, and then you somehow force the optimization to in the end basically push the results again to something that is discrete. So for example, these tricks are used in topology optimization, for example. So there are ways for doing this, but I think also in the end, also for many projects, very often, the difference between something that works sort of okayish and something that works really well, picking the right representation somehow and trying to basically map the problem into a good representation that is somehow, on the one hand, when you have a design problem, for example, easily understandable by the human, where a human can edit it, but also the machine at the same time, I think is also something really valuable to do and is really worth also the research effort. And very often, we also during the years when I think back, we basically after every project we thought, okay, we figured out the magic formula for doing it. Then there was the next problem, and it turned out, it's not so easy, and there was actually quite a bit of research required. But this is also, I think, therefore, it's also really an exciting area where, if you put in a little bit of research, I think you can find actually quite nice solutions. I don't know if this directly answered your question.
No, I think the first part. Thanks.
Yeah, thank you very much, Bernd, for the very inspiring talk. I have two questions. The first, can I get my hands on the unified procedural graph to try it myself? That's the first question. And the second is a small question that just bugs my mind for the last project. Is it always staying a trefoil knot, or is it allowed to move through itself to become an unknot?
So, first answering the second question, so it's a continuous optimization. So it's always basically this curve that stays together, but, we do have a collision detection. So it's in some sense, it always keeps that topology.
Okay. You can't do a circle with it.
Yeah, basically you would need to start with a circle. If you start already with a circle, then that would work, right? But in some sense, yeah. And for the second thing, so we have not yet publicly released it because we have some very specific ideas for cool follow-up work but in theory, yes, yeah. So yeah.
Any other questions? I see Benjamin.
Thank you, Bernd. Very inspirational talk. Now, in your talk, you only at the end you highlighted also the vision of spatial computing, and maybe you could give us more information about your vision, because I think that's an open question for us. How this will immersive technologies, immersive design will influence the design process, both on the client side maybe and on the designer side.
So I mean, I personally have very high hopes in this area, and I'm actually very convinced that I mean this will really fundamentally change also, even not just for design, but in general, how we interact with the environment. I mean, so far the problem was making good hardware, right? So basically that you have a device that you really like to wear, or where you don't feel dizzy when you wear it for a longer time. I mean, making such a hardware is a really hard, a very difficult problem. And I mean, basically big tech is already now for some years investing very heavily into this. Also because there is actually the belief that potentially at some point, if this becomes lightweight enough and so on, that it might actually be sort of the next wearable device that potentially replaces the phone or the laptop. And yeah, so I think basically there is at the moment Apple, Meta, and so on, they're very heavily investing in this. It's a very difficult problem, but I mean, they for sure they are making very steady progress. So I believe actually very soon, I mean, very soon, in the next couple of years, actually, we will see devices that are very high quality and that are, that you really want to wear. And it's a game changer, I think, in multiple dimensions. So first of all, of course, you can, have immersiveness, right? So you can really experience things in a very different way. You can also maybe do like collaborative design and so on. So this is one dimension. Maybe this is already the dimension that is already quite possible nowadays. But then also the other thing of this device is also potentially, it can actually really sense and understand, first of all, the human, the wearer, right? What are you doing? What do you want? It can actually see the environment. So in some sense also it can also understand the environment, right? And if you're on a construction site, maybe suddenly you have a device which in a very smart way can analyze the surrounding. And with this can give you also much more information and basically enable you to do things together with the device that is not possible nowadays. And also there, right? I mean, certain things are simply difficult at the moment. I mean, having really reliable scene perception, or even like reliable human tracking and so on, it's somehow coming, and we really see like also there I would say almost like exponential progress, but there is still also really a gap, so that this is really that you can deploy this basically as a product, right? But I really believe all these dimensions, and then together also with the machine very close to you, and new ways of also interacting with it, with language and so on, right? I think also that's a very new dimension that somehow is really a game changer, how one interfaces with technology. So I really believe there is actually huge potential in there, but so that it becomes more widespread, it needs basically also this advancement on the hardware side, which is simply when people fighting with the physical reality and physical limitations simply, and so it's difficult, but there is progress, and I'm quite confident that also probably, I mean, this is maybe 5 or 10 years away, but we will have glasses maybe similar as Anton is wearing them, but with really, binocular displays, immersive displays, and so on, that can also sense what you're doing. And I think, yeah, so this will for sure change things, right? Also, for example, just on the construction site itself, right? Maybe even like having a system which very precisely gives you advice on what you have to do and checks quality and so on. So I think this is all probably quite disruptive. So I believe we will see many things there. And I think now is the right time to do research in that area. And there's many things that so far are unexplored. And there's really, I think, a really huge potential, right, to somehow be a leader in the field and define the future there. And it's both then on the research side, potentially also with startups and so on. So also I think with that, it's a very exciting area to be in and to explore. And it's the right time now, I believe, to do that.
Great, thank you very much for the questions from the audience, as well as the answers from Bernd. With that, just to respect the time a little bit, I think we're a few minutes over the hour, but I would like to then say thanks from the side of Design++, and we look forward to seeing you next semester for our upcoming speaker lineup. But before we open up the apero, I'd like to hand the microphone over to Benjamin for a few words.
Okay. Yeah. So that's for me a bit the unfamiliar role of the deputy head of the institute, but as such, as Philip is not here, he has a tiny but wonderful excuse not to be here today. I would like to express my warm welcome to you in the name of the entire Institute for Technology and Architecture. We are very happy to have you on board, Bernd, especially after seeing now your projects in the lecture, as a new colleague with this expertise that makes that, and I think you pointed it out, also very excited about the future. I keep it short, but I think it's a very good sign already that already some first collaborations emerged, and also with us personally. So that's very exciting. And I also know that Bernd acquired a new coffee machine, so I think you will really soon have a lot of exchange. You should also once tell us a bit what we have to do to win the Academy Award of Special Effects. That's something you skipped in your talk. I mean, I keep it short, but I know that besides all the collaborations that are also happening in the context of Design++, there will be also a kind of friendly competitions between the different departments, computer science, DEBAUG and DEARC, about who gets most of your attention. And that already leads me then to what we did here as a DEARC. We prepared a little courtesy over there, the apero. I heard in your lectures that you mentioned once, and that was for me the most important sentence, of course. You said you wanted to pop a bottle of champagne. So we have some wine prepared, and you said there's no free lunch, but there is a free apero for you. So let's jointly welcome Bernd here to ETH, also back to ETH, of course, and to ITA. Warm welcome.
Thank you very much.